Welcome to class. So last night you guys watched a pre-lecture on Introduction to Matter, specifically the types of properties and characteristics. We have 4 categories that we label or identify properties of matter in, and that was extensive / extrinsic, the kind of equivalent in name. Okay, intensive / intrinsic. When you think of intensive / intrinsic properties, think I properties, identifying properties. Intensive properties are always unique to the substance because it doesn't depend on amount. It's inherent to its either nature or reactivity. Okay, and then you have the categories of physical versus chemical. Physical obviously being rooted in the physical, right? Physical, right? And then of course, yeah, I get it. And then chemical, okay, being rooted in its reactive nature that is only usually observed under a reactive environment. So you got to do something to it, right? Kind of like people sometimes. They seem real chill until you put them in an unknown environment. That's when you get to know them, right? So, and then we talked a little bit about, okay, let's see, what else did we talk about the pre-lecture? Oh, how at the macroscopic and microscopic level of organization. So we talked about, okay, element versus compound. An element is a pure type of atom, and a compound is a bonded, group of atoms that are usually different, okay? Not always though. You can technically have a compound made of the same element, okay? At the macroscopic level though, if you had a element at large amounts, it would be called a pure substance, or a one type of composition, one type of compound at massive, like water. Okay, that would be considered a pure substance. Okay, then we talk about mixtures, homo and hetero. Okay, homo and heterogeneous. These are pretty obvious concepts. Okay, the big idea here is solute and solvent terminology. Aqueous is super important, because most of your reactions will take place in an aqueous environment, a water solution environment, okay? And that is actually so important that we include that in our chemical reaction notation because it's that significant. And then we have heterogeneous. Basically, if you see it and it looks different, it is, okay? And now what we're going to do is we're going to take a few moments to look at different methods of separation. This is kind of a lab expose on how you examine and work with different types of mixtures. We have my lovely actual TAs, by the way. These are my actual TAs, but they've been working in the back room prepping all this stuff, that I've set up a series of demos for you just to give you visual, okay? There's a lot of lab FRQ questions in the AP exam where it's just helpful to have the context of what they're talking about. So when we look at this, for separating mixtures, one of the first ways that we can separate mixtures is through, specifically physical separation, right? Is through sorting. So you can sort by size, you can sort by color, you can sort by other things. We tend not to do that too much, but if you really need a visual, let me show you. Okay, let's see. We can sort.
Lovely and completely unnecessary demonstration. You can sort the red glass discs and separate them from the other colors. Basically, you just do this by hand.
Yep, pretty much. Yay. Here's the thing about sorting. At the chemical level with instruments, we actually use advanced instrumentation to sort by size. At the AMU, atomic mass unit level, we sort through fragments. We literally shoot beams at samples and we split them. And then we sort and take a spectrum of it and we analyze it. You're going to learn about that tomorrow. Okay, but at the macroscopic level, it's pretty obvious. You did it as a 3rd grader, maybe even if you were a good child as a 5-year-old, clean up, right? But that's pretty basic. So honestly, I'm just gonna write, you know. You got it? You know what that means. Okay, now what about filtration? Filtration is a little bit more unique. Filtration is using, physics people, your favorite force, gravity. Okay, gravity to separate usually different size particles and specifically different states of matter of a solution. So for example, if you have a sandy sample, like have you ever guys tried to get sand off the beach and you get water too with it? What might you do? You filtrate it. If you are a coffee lover, what do? You filtrate out the grinds, the coffee grinds. So like here, what we have is we use a, well, that's interesting. We normally have a special filter paper. So let me go ahead and show, but they got sketchy. They did sketchy chemistry and they created their own filter paper with a paper towel. And then what you would do is you would pour in your mixture, usually heterogeneous. Usually it's quite obvious. Oh, I'm sorry. You kids are in the video. Sorry. And you would just simply let gravity take its time to separate out the different size sediments or the different states of material. You're like, this is so obvious. It is. It is indeed, folks. And here's why we like it though. Sometimes it's the simple methods that are the most important, okay, that get you the best results. You don't always have to complicate everything. So filtration is taking advantage, right, of particle or state of matter difference. And with gravity filtration, what we do is we might hook it up to what we call a Buchner funnel and a special filter paper that has different size holes, essentially. It's a different type of grading. Gravity filtration can also turn into a special category known as vacuum filtration. I don't know how to spell vacuum. Filtration. Did I spell that right? Well, if you close your eyes, one of those U's look like C. So vacuum filtration. And so what we do is instead of just waiting for gravity to take its sweet time, we actually hook up as suction and we suck a vacuum of space. So we increase the rate of the gravity separating the liquid. So all that is what we're going to do is we're going to use, basically, we're going to create a vacuum. In flask to accelerate the separation, right? To accelerate the separation. Vacuum filtration would be awesome to do with you guys if we actually had the hookups, but we don't because we're broke. Yeah, we're broke. And so the next type of separation, again, very much based physically, but notice, this is an actual physical intensive property. Magnetism is unique, okay? It's an identifying property to the substance. Magnetism, okay, is obviously using the magnetic pole of things, okay? So, what we have here is we have iron fillings in a sample of sand, and using your magnet, you can separate out the iron from the sand. Wow, excellent. So, I was trying to make this more exciting. Is it working? No?
Yeah, we're getting all the very
basic
ones out.
Yeah. Wait for it, guys. It gets better. Okay. I will do my darndest to make this an exciting class. So, magnetism using north versus south, attractive, repulsive. I can't spell today. Attractive versus repulsive. Okay, chromatography is the next one. Chromatography is really useful. In fact, it was my main purification method as a research student. So chromatography, what this does is it uses solubility principle, okay, and polarity. Oh, it just moved on me. Jeez. And polarity to separate liquids. To separate a mixture of liquids. Liquid mixture. I realized I put my dot like 4 letters later after the I. I apologize. It's just a bad habit I picked up. So chromatography, you guys will eventually learn in unit 3. There's a term or there's a motto where we say likes dissolve likes. Polar substances are soluble with one another. Non-polar substances are soluble with one another. Likes dissolve likes. Likes take up likes. Likes travel with likes. So what we do is if we have a solution with 2 different liquids that take on a different characteristic, Okay, we can use another liquid that's similar with one of the liquid's characteristics and have it basically drag out the liquid that it's similar with and leave the other liquid behind. We call the other liquid, by the way, usually the mother liquor. Yeah. Anything left behind in a solution with centrifuging or decanting or chromatography or anything like that is called the mother liquor. Okay, so for an example, let's see a general setup. There are two ways you can do chromatography. You could do it at the micro scale. So at the micro scale, you have a piece of paper and you put a sample of, you put a sample of your personal unknown, maybe it's your product, and you put a sample of your reactants. And what you do is you put it in a solution that when you drop it into the solution carefully, the solution travels up and it takes your dotted samples with it, whatever drops of sample you put on that line, and you literally measure what we call the retention factor. How much does that original dot move up? And then you measure that retention factor distance, and that tells you something, one, about the characteristic of your liquid and the presence of your sample, okay? It is totally right now very much abstract to you, totally okay. And it's something that we're probably gonna do at the end of our time together when we do a massive lab month, which is May, after your AP exam, all right? But large scale chromatography looks a little different. So large scale chromatography involves a very massive setup that we don't have image here, but where we take essentially, may I borrow this? Oh, not quite the right tube that I want, but this idea. Ignore these handles, okay? We take a tube and we fill it with sand in multiple layers of different basically grains, okay? Sometimes we fill it with silica gel. Would you mind holding this up on camera for me? Sometimes we take a tube. Whoa. Sometimes we take a tube like this and we fill it up with sand or silica gel of specific particle size. And we send a liquid, we pour our sample in and we send a liquid through that would carry our sample that's in an impure mixture, because it's caught in other byproducts and so forth, or unreacted reactants. And we have it travel down the sand and tube and silica gel, and only the product comes out with the solvent that you put it in that was similar to it. And then you purify that. Okay, so again, we'll probably address that later on. It's a different hookup, but it's a similar idea of a glassware that you drop things down and you can never let the sand dry. It's a huge method. I did it every day, multiple times a day when I was doing research. Okay.
In this case, we just have inks that are being drawn up with alcohol, and we'll look at that one again, but basically you'll see the inks separate out.
Yeah, so micro scale versus large scale chromatography looks very different, but it's based on the same principle. Okay. And then we got density. Okay. If any of your parents are wine lovers, okay, they probably do decanting. They probably know about the decanting method in wine. But with density, obviously, what you do is you separate based off of density, right? The lower density floats, the higher density is toward the bottom. And then what you can do is you can use a separatory funnel. Do we have to grab a separatory funnel? Ooh, no worries. You can use a type of funnel that you can literally just pour off the different layers and then just stop. And you just have the heavier liquid.
That's what the burette's for.
Perfect. So let's go ahead and look at decanting as a method using the separation via density.
In this case, this is oil and water. Oil obviously floats on water. It's less dense. It's closer, I think.
You've emulsified it through mixing. You've created basically oil bubbles surrounded by water. And now you're going to let it separate. Zoom in. Sorry, Sam. You're also Evan is now behind it. And you're going to let it separate and go ahead and give it a little flick. Get the bubbles. We flick a lot in chemistry. We flick the glassware a lot. And go ahead and filter it out. This, by the way, this setup is called a beret. We actually technically use a different glassware, but the concept is similar. The other glassware is a separatory funnel, but it's a little tedious to get out, so no worries. My TAs are very creative. I appreciate it.
Also don't know where anything is.
It's true. They are learning the stockroom. I'm the stockroom boss, and so I like everything exactly Okay, see, notice how you can separate and you just keep going, stop. And now you can just have that mother liquor and then you can drop the rest of it into a separate container and you have separated your liquids purely based off of density. Very convenient, very simple. Glassware, surprisingly expensive, but so density, here you're taking advantage of differences in density. It is a very simple method. We love it. Okay. Decant versus centrifuge. Joy, would you go to the back and grab that weird shaped thing? That is a centrifuge. Okay, so decanting is even simpler method that is often, again, it's under the category of density. Decanting is you literally just wait for your sediment to settle and you pour it off. That's the wine method, okay? That's the wine method. You wait for the sediment of your wine and then you let it rise to the top, you pour it off, and now you have your beautiful sample of wine, which none of you are drinking because none of you are legal. And then with centrifuge, okay, what we do here is sometimes this is particularly useful in bio. Okay, what we have is a centrifuge machine. And sometimes when you want to separate white and red blood cells, right? What you need to do is you need to have vigorous agitation to get them to separate. Okay, so what you do is you put your sample in here. If I can get the lid off, nope, can't, but you would. And you put on the spin, okay? And let's see if I can just turn on the spin. It's not a great sound. So if there was a bio in there, it would spin and spin and spin and spin. Spin and spin and spin and spin. I feel like the 1980s when they just did like film off of like a video camera. And what you would do is at the end of your spin, you would have a tube who had sediment on the bottom and liquid that you could just pour off, also called the mother liquor. Okay, it's actually, that's the most common term, is the mother liquor is used most commonly with centrifuge. And you'd get a sediment or your dense different particle, or maybe even your suspension, right? Remember, heterogeneous mixtures can be in suspension. You just have to wait for it to settle. You accelerate that settlement by creating an excessive spin that separates them, okay? So here, decanting, can I write this wine? Like wine connoisseurs? It's a wine method. It's like literally you pour off the top, and then centrifuge is this is particularly useful for suspension. You accelerate this separation via spin. Okay, the final method is distillation. Now, this is a super cool method that we will not probably do in our work because we just don't. But this method is based off of boiling point, separating off by boiling point. So what you're going to do here is you take advantage of liquids with different boiling points. And what you do is and it's significant different boiling point, not like 98 degrees and 99. Like good luck trying to control that, right? Like 70 degrees and 110. And you have a sample of a mixture of two liquids and you say, okay, I'm going to boil this sample. So for example, let's say you have, okay, a liquid in here. Ooh, all right, in here. And it's two liquids. You would boil this with a Bunsen burner below. Oh, it stopped? That's not good. It's still recording. It says it's still recording, but how odd. Oh, let me screen share again. Hold on. Easy fix. Screen share. That's a really great angle. I appreciate that. This is going on YouTube, but that's okay. Everyone's gonna see it. Okay. So hopefully we have it back. So what you have is a mixture of liquids, okay, here. And you put a Bunsen burner or something and you boil it. Then what you do is you put it through a condenser tube. This condenser tube will take that initial liquid vapor, condense it back down to a liquid and deposit it down into another flask. And then you have your two separate liquids. And in the process, you purify it at a high level because what happens is often your condenser tube also has a filtration part where it catches any debris. It's a really handy dandy method, okay?
to cool down.
Excellent. So the more volatile, by volatile, that means easily boiled. The more volatile substances, the more readily it evaporates, i.e. the lower boiling point substance will go first, and it will be the one that you find in the new flask. Okay. So that's kind of your little overview of separation methods via physical characteristics. So moving on to matter at the particulate level, we say that an element is defined as it only contains, okay, one type of atom. So we can have monoatomic elements like a single iron atom. We can have polyatomic elements. For example, we look at a really good example is your diatomic molecules, Br, bromine 2, iodine 2, nitrogen 2, let's do chlorine, chlorine 2, hydrogen 2, oxygen 2, and fluorine 2. These elements, these diatomic elements, are a unique example of polyatomic elements where they bind to themselves. When you think they're alone, they're actually not. Okay, so you would never just have a free H atom floating out there. If there's an H atom free, it's with its buddy, another H. You have to memorize these, by the way. These are very useful to memorize. You want to memorize them. And the little shorthand term is Brinkelhoff. Mr. Brinkelhoff. Brinklhof. Brinkelhoff. Okay. Some other polyatomic atoms, you'll encounter them through problems, but I forgot to write the definition. They're many atoms of same kind of element. Right, two or more, many atoms, yeah. So allotropes are various forms of the same element. So oxygen is a great example. Allotropes are elements that have various forms of the same element. So for example, oxygen, ozone, okay, would be a great example of two allotropes of oxygen that are also polyatomic elements. There will be another type of polyatomic that you learn later, okay? So what about compounds? Okay, compounds are defined as containing two or more different type of atoms, different type of elements, chemically bonded together. Note the word I should add, chemically bonded. Okay, so we can have organic compounds. That was my specialty. Okay, that was my specialty, organic compounds. And these always contain C, carbon, or H bonded together. My personal research was actually developing, when by me developing, I was just the lab rat guinea pig, making sure we had enough trials run. But developing a new method to create an unfavorable mechanistic movement of electrons to increase the rate of production via a new mechanism that would increase the rate of drug making for a particular popular structural dynamic in a compound. So it was interesting. It was I don't even know if it was super successful. I wasn't there. I wasn't there for the end. It took like 6 years with a bunch of us college students rotating through. Okay. But an example of this would be your favorite C6H12O6. And I realize that my C looks like a 6. I will fix that. Okay. Inorganic compounds are basically everything else. Glucose? That's okay. You made me question myself too for a second. I was like scared. I was like, oh no, is it wrong? Everything else not containing carbon and hydrogen. Okay. So example. C and H. Yeah. H2SO4 is technically inorganic. Your metallic physical chemistry, material chemistry. Emin, you said you're into meteorology or materiology? Mineralogy, that's right. Your handwriting was real rough. Mineralogy, you would be in the inorganic world. Yes. So then we categorize compounds as ionic or covalent. Ionic compounds, okay, are bonded via charge attraction. I know my handwriting gets worse. You'll learn to interpret it. Okay. So we can have binary. Okay, we can have binary ionic compounds where it's just two types of elements. So one example would be NaCl, your table salt. And then you can have non-binary, which is like, oh, well, we could do that. No, I won't do that to you. Let's do calcium carbonate. Okay, that is a 3-element ionic compound. Calcium, carbon, and oxygen, calcium carbonate. Okay, then you have covalent. This is bonded via sharing of electrons. And we're going to study that real closely later. Okay, and an example would be, by the way, glucose as well. C6H12O6. Most organic compounds are covalently bonded, but not all. Lots of inorganic compounds are ionically bonded, but not all. Again, you do not want to pair these necessarily. This is not a set pairing. There's just maybe a general trend, but there's always exceptions. So, right? So, we can actually, through mass, identify and determine the composition of a compound. Okay, so let's say experimentally you did a little test and you, yes. I see how that looks like a delta sign. That is H2SO4. O4? Huh? Yeah, sulfuric acid.
I thought it was an 8 and I was really confused.
Or bisulfate.
What the hell?
Oh, that got on tape. Cool. Yeah. Sorry, if you ever find that my handwriting is a little too fluid for you, kind of like my driving, just let me know and I'll do the best I can to fix it. Or you'll just learn a new language. Yes.
So when that's CL, right?
Yes, that is supposed to be a Cl, NaCl, salt. That is indeed the intention of that writing. Okay, so all samples of a given compound have the same composition by mass. Okay, this is actually a law. It's called the law of composition. And what we say is that the composition is what the matter is made of. That's the official definition. What is made of. And we particularly pay attention to the ratio. For us, we care about the ratio of atoms. That's like our focus. Okay. So for example, H2O, our composition would be eventually quantified by mass, but we'd be looking at a ratio of 2 H's and 1 O. Our quantification, that looks like 10. I realize that. Oxygen, okay? Our composition numerically should reflect this same ratio in order for it to still be a water molecule. Now, sounds obvious. You're like, obviously water is going to be H2O, but scientists had to give it a law that, you know, water can't be suddenly H3O and still be water. That was kind of the big idea. Now, how do we do this mathematically? And by the way, this tends to be a very simple MCQ or FRQ if you're lucky, okay? So let's say I have a 550 gram sample of chromium 3 oxide, an ionic compound. That is its chemical formula. And it has 376 of those grams from chromium. Okay, and I ask you how many grams of chromium and oxygen are therefore in another sample of 212 grams, assuming it's the same compound. So what we do, if probably all you mathematic people know where this is going, is we say to ourselves, okay, well, let's first take what I know. I can easily figure out the percentage of chromium given our initial information. Okay, initial information. So I say that's going to be equal to 376 grams of chromium over 550 grams of the entire sample. Chromium, yeah, oxide. So I realized that my composition by mass that is unchanging for this compound is going to be 68.4% chromium. Now, did I do it to the correct sig figs? I did indeed. 3 sig figs. Okay, so then I can say to myself, well, I know if there's that much percentage of chromium to be 100%, that must be the rest of the oxygen. So oxygen must be, okay, that looks like 0. I realize that too. Okay, is about 31.6%. So then we take this ratio that we have established in a percentage and we say to ourselves, okay, well then what must be true about the mass percent composition of the same compound, just a different sample size? Remember, mass is extrinsic. It's totally dependent on how much you cut of in a sample. And so we would never use it as identifying until we turn it into a percentage. Ratios become intrinsic. Okay, so then we get for 212, I'm assuming you all know how to do this, for chromium, you would say times 68.4%, and you would get a mass of what? I didn't finish the math. I gave up. In my prep. What is it?
You gave up in your prep?
Yeah.
It's like a calculator, just plug it into the calculator.
I had long nights when I was prepping this. So does someone want to solve it for me? 14,000? It's a percentage.
No, yeah, but what?
145.008 sig figs. 145. Okay, chromium. So then we don't even have to do the other math. We just do 212 minus 145. Please, someone do that. 212 minus 145. What is that? 55 plus 12, 77? 67, thank you. Okay, and so 67.0 for 3 sig figs. Okay, grams of oxygen. Okay, so that's all I actually have for you in class. If you find yourself not confident, there is a link, a hyperlink to a video walkthrough with Tyler DeWitt. Yes. Yes.
This is more like to sig figs. Do you round to sig figs or do you just truncate?
You round up to the last sig fig. So if my sig fig was, let's say that 145.008 and I wanted 5 sig figs, it'd be 145.01. I would round accordingly, just like normal. Excellent. Yes.
What do you do if you can't have the correct amount of sig?
You write in scientific notation. Scientific notation allows you to adjust the sig figs while keeping the same value, which, by the way, is your quiz tomorrow. Okay, so good job, guys. Bye. Sorry for all the crazy videoing.